Well, now let's look at the end behavior of rational functions. Since a rational function is just the quotient of two polynomial functions, and using the ideas of end behavior, when we evaluate the limit, we can take the limit as x approaches infinity of the leading term of each polynomial. So the limit as x approaches infinity of 5x minus 9 over x squared plus 1 would be the same as the limit as x approaches infinity of 5x over x squared. And at this point we can simplify the fraction to the limit as x approaches infinity of 5 over x, and we cancel the x's. Here we have a finite value in the numerator and a variable in the denominator that is growing without bound, so the limit is going to go to 0. This also means that we would have a horizontal asymptote at y equals 0. Let's look at b. We have the limit as x approaches infinity of a rational function. We are allowed to use the end behavior idea, and so we'll rewrite the limit using the leading terms only. Reducing, we can cancel the x's. 80, now we can evaluate this limit. 80 divided by 20 is just equal to 4. So the limit of this, so once we simplify, we have the limit as x approaches infinity of a constant, and that constant is 4. And so the value of the limit as x approaches infinity is 4. Therefore, there is a horizontal asymptote at y equals 4. Okay. Let's look at the third. C. We'll rewrite. We're going to infinity. We have a rational function. We get the limit as x approaches infinity of 3x squared over x. When we reduce, we get the limit as x approaches infinity of 3x, which is infinity. So if as x approaches infinity, y does not, or the function does not approach a finite value, there is no horizontal asymptote. Now in the last example, there was no horizontal asymptote because the exponent in the numerator was larger than the exponent in the denominator, the exponent on those leading terms. But there is something called the slant asymptote that occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. And I'm just going to show you one of these. I'm not going to spend a lot of time on this, but I just want to expose you to one of these. And then we'll move on and look at some other end behavior. So when the degree of the numerator is 1 more than the degree of the denominator, we're going to divide. We'll take 3x squared plus 8x minus 5 divide by x plus 1. So I multiply x by 3x to give me 3x squared. I multiply back. 3x times 1 is 3x. Here you're going to add the opposite, so that cancels. 8x minus 3x is 5x. Bring down the minus 5. Then I look and say, what do I multiply x by to give me 5x? It's going to be plus 5. 5 times x is 5x. 5 times 1 is 5. And we add the opposite again. Negative, negative, that cancels. A negative 5 plus a negative 5 is negative 10. And so now what we have is the limit as x approaches infinity of 3x plus 5 minus 10 over x plus 1. And so what ends up happening here is that this portion of the expression is going to go to 0 as x goes to infinity. And what's left here is the behavior of the function. The function itself as x gets really, really large, is going to behave like the line 3x plus 5. So the slant asymptote would be y equals 3x plus 5. And so I'm going to open up the calculator. And what I've done is I've put the original function in for y1. So I've got y equals 3x squared plus 8x minus 5 in the numerator, close the parentheses, and then we would divide that by the x plus 1. And then in y2, type in the 3x plus 5, and then we'll just do a zoom 6. We'll do a standard graph, and we can see the function, and now we can see the asymptote. And so you can see that the function starts to behave or hugs the asymptote. And I could zoom out on this a little bit if I zoomed out to get a better idea of how that asymptote is working. There's your function, and here comes your asymptote. So yeah, the function, as you zoom out, you can see it that the function eventually behaves just like the slant asymptote, or that linear. So before I have you try a couple of problems, I'm just going to summarize the ideas for end behavior of rational functions. So you've got a rational function with a polynomial in the numerator and the denominator. If the power of the leading term in the numerator is greater than that of the denominator, then your limit, the limit of the function as you go to positive infinity or negative infinity, is 0, and y equals 0 is a horizontal asymptote. If the leading term's degree is the same, then your asymptote is literally just the ratio of the coefficients of those leading terms. And if your numerator's power is greater than your denominator's power, then the limit is infinity or negative infinity, and so you have no horizontal asymptote. Remember, in order to have a horizontal asymptote, the limit as x goes to infinity or negative infinity has to be a finite value. And then lastly, there was that slant asymptote, and that is a special case, and that occurs when the numerator's power is exactly 1 more than the denominator's power. Your function starts to behave like a linear equation. Right, so pause the video, and what I'd like you to do is use end behavior and limit notation to find the following limits. And then start the video up to check your work. I'd also like you to state any equations of horizontal asymptotes. Alright, so the first function, we've got a rational function. We know that the limit of this function is going to equal the same as the limit as x approaches infinity of 12x to the 8 over 3x to the 8. We can reduce this. The x to the 8's cancel, and we end up with the limit as x approaches infinity of 4, and the limit of a constant is that constant. So your asymptote, your horizontal asymptote, is y equals 4. Now let's look at the limit as x approaches negative infinity of 12x to the 8th over 3x to the 8th. Now, in this problem, still the same idea here. The limit of this expression, or this rational expression, is going to be the same as the limit of the leading term. The same thing is going to happen here. The x to the 8's are going to cancel. So you get the limit as x approaches negative infinity of 4, and the limit of a constant is going to be that constant no matter what value you're approaching. And so same function, whether we approach positive or negative infinity, we get 4, and our horizontal asymptote, we already said, was y equals 4. Alright, let's look at this one. The limit as x approaches infinity of negative x to the 7th plus 12. That's going to equal the limit of the leading terms. We can cancel one of the x's, so that would give us negative x to the 6th. As x goes to infinity, remember this is a negative x to the sixth, so if I just had x to the sixth, that would go to infinity, but negative x to the sixth, that's going to go to negative infinity. And so there is no horizontal asymptote. We knew that just from looking at it, if the degree of the numerator is greater than the degree of the denominator's leading term. All right, last one. The degree, the limit of a rational function is the limit of the leading term. We can cancel the x and x with each one, and so the limit as x approaches infinity of this is going to be 0. I'll put that underneath. It's going to be 0, and your horizontal asymptote would be y equals 0.